we're gonna be taking a look at free fall versus retarded fall. And both of them are differential equations, and we're gonna see the form that each of them has. So for free fall, if we start with just Newton's law in one dimension and we measure y downwards, then we can say that ma, the acceleration, is just the acceleration of gravity, so ma equals mg. G is a constant. The other thing that we know is that the acceleration is just the time derivative of the velocity, and so we can replace that here. But before we do that, we can see that we can cancel an m on both sides, which means we have dB dt equals g. Here we can see that we have a constant on the other side. We're gonna integrate on both sides. One side is gonna become dB and the other side is gonna become g dt. I need more space here, and so I'm gonna do this here. So if we integrate with respect to time on this side, now g doesn't depend on t, so it's just a constant, and we're gonna integrate t from t equals 0 to t equals 1. We could just call it t, which is probably a better option here. And on this side, we are going to integrate from b naught, so an initial velocity, to some other velocity b. This, after integration, this becomes just b from in one side, evaluated at b naught and b, and this has to be equals to, again, g t evaluated at t equals 0 and t. On this side, it will become final, which is b, minus initial, which is b naught, and that has to be equals g. And then t equals final, it's just t, and then minus initial, which is 0, so t minus 0. So if we move this b naught to the other side, we can see that we end up with b equals g times t. Adding that term to the other side leaves us with the velocity equals g of times t times b naught. And this makes sense because whatever initial velocity you have will be incremented as time passes by gravity. So as you fall, you'll fall faster and faster and faster. Now this doesn't take into account air resistance, and so here we can see that this is a linear equation. So if we want to think about it like y equals mx plus b, different b, you can see that this is just a line, right? Now remember that we get this from the equation ma equals mg, or just a equals g, but this doesn't take into account, again, air resistance. So if we want to take into account air resistance, we have to add an extra term, another force, right? So if we think about air resisting as increasing as you increase in velocity, basically if the faster you're falling, the more air resistance you'll experience, then that means that the force of air resistance, I'm just gonna abbreviate it AR, is gonna be proportional, not equals to, but proportional to the velocity, right? And we also know that the velocity is just equals dy dt. If you want to make this an equal sign instead of a proportionality sign, what we do, we call it FAR is equals to, we need a constant of proportionality, which is, we'll choose k and then b. So this means that the force of air resistance is equals to some constant times the velocity. So the faster you fall, the stronger the force of air resistance is going to be. Now we're missing something here though, because as we're falling downwards, our velocity increases, but this should decrease that velocity. So instead, this is going to become negative here, but that's why the negative is there. This force it decreases the velocity instead of increasing it. So then, having all of this together, our new ma is going to look like ma equals mg. Now we want to add it, but in this case, because that's negative, then we're subtracting k and then b. The other thing that we can remember is that the acceleration is also equals to m dB dt. Let's rewrite this first right here, which then it looks like m dB dt is gonna be equals to the mass times gravity minus the constant of proportionality times the velocity. Now there's a lot of constants floating around, and so to make it simpler, what I'm going to do is I'm going to divide both sides by m. dB divided by dt is going to be equals g minus k divided by mb. Now I'm going to define a new constant to make it even simpler, and that constant is going to be equals to k over m. Now what I want to do is I want to integrate dB g minus k over m times b is going to be equals to dt, and also I'm going to replace this with cb, since we define a new constant there. And this side I want to integrate in respect to b, and this time with respect to t, and so here I'm going to integrate from t equals 0 to t again. Now this side I'm going to use substitution. U is equals to g minus c times b. du, taking the derivative of g is a constant, so I don't have that anymore, so I'm left over with negative c dB. Now I want to solve for dB so that I can replace it, and so dB is equals du divided by negative c. So what I'm gonna do now is I'm gonna say that dB is equals, well, let's take the negative 1c outside, negative 1 over c, since it's a constant, and I'm left with du inside. On the bottom, g minus cb is just u, and since this is used with respect to t, I just get t on this side, since it's from t equals 0 to t. Now this here is just the natural log, negative 1 over c. I also have a constant, let's call it b1. This is equals used to t, also this should be inside parentheses. I don't know if that's super clear there. So I'm gonna multiply times c on both sides, or negative c, so I'm left with negative ct is equals the natural log of u plus b, which if we replace u by its actual value, we know that u is natural log of g minus c times b plus b. I want to be able to get rid of this natural log, but before I'm going to move this constant integration to the other side, so I'm going to call it negative c t minus b is equals to the natural log of g minus c times b. Now this constant here is just a constant of integration, so it doesn't really matter what sign is for now, but instead of just making it positive, I'm going to rename it and make it plus b. Actually, let's call this b1, which we already had done on top. I forgot about that. Then this new one here, since it has absorbed the negative into it, is gonna be b2, and that's still equals to the natural log of g minus c times b. To be able to get rid of this natural log, what I'm gonna do is I'm gonna erase both sides with e. So on this side I'm left with e minus c times t plus b. Now on the other side, then I will have just g minus c times b. Now this b's here, what I can do is, because they are being added, this means that it's just e to the b2 times e to the negative ct, and so that is equals to g minus c times b. Now this one here, that is just another constant, it's some number. I'm just gonna call it a. So then a e to the negative c t is equals g minus c times b. Negative cb is equals to a e to the negative c t minus g. Now I need to divide by negative c so that I can get rid of it on this side, and so I am left with b of t. The velocity is a function of time, and so this results in a e negative ct minus g all over negative c. The next step that I can do is figure out what a is. Let's say that I will assume that b naught, so at time t equals 0, the velocity is equals to 0, and so this means then that this side is equals to 0, and that has to be equals to a. Anything to the 0th power is going to become 1, and so I'm just left with a, and then I have negative g still and negative c. Now if I multiply both sides by negative c, I can see that I'm just left with 0 equals a minus g, or in other words, a is equals to g. Now since I have figured that out, then I can replace a with g. So this means that the velocity is going to be equals to g times e to the negative ct minus g, all of it divided by negative c. If I pull out a negative from these two terms and also a g, this is also equals to g divided by c. I'm left with a 1 and becomes 1 minus e to the negative ct. So let's rewrite it again just to make it clear that b of t is equals to gc times 1 minus e to the negative ct. We can compare it to the previous one, which is all the way up here. Where is it? And whoops, that's not it. Here it is. B equals gt plus b naught. gt plus b naught there. As we can see, they are quite different. This does not look like y equals mx plus b, so it's not a line. And something that we can do just to see what's going on with this one is just free fall with no air resistance included. So this means that as time passes, the velocity keeps increasing and increasing forever. Now this one, what happens as t approaches infinity, basically at a very large amount of time? Well, what that means is that, well, I'm gonna do that, is equals to g divided by c times 1 minus what? Well, this one here will actually become 0. And so what I'm left with is gc times 1, which is then just g over c. So this means that no matter how much time passes, as time approaches infinity, the velocity will approach g over c. So we can see that here we have a limiting velocity, whereas here we don't. Velocity keeps increasing as time increases, and in here it doesn't. It reaches some value, which is g over c. So when people talk about terminal velocity, this is what it means. There is some theoretical limit to how fast something can move. So right here I am in Wolfram cloud. So here I'm using dsolve. Let's look at this piece here, and really what dsolve is, it solves a differential equation for the function u with independent variable x. So here I see that I want to solve for b of t, so the velocity, and I'm giving it here my differential equation, which is the one that I solved earlier. But let's see what we get, and we can see that we get gt plus c1. Now let's take a look at actually what that looks like, and we can see again y equals mx plus b, right? The solution gt plus some constant is is similar in form to y equals mx plus b, so it's just a line. And now let's look at the second one, the one which is the one that takes into account air resistance. And again, I'm using dsolve here and simplify. Simplify just makes it a little nicer to read. Let's see what we get there. And also I am plotting it at the same time, so we should get the answer, which is this. But now the more interesting part to look at is the graph. So as we can see here, the velocity, and here it's not showing, for some reason it's not showing, but the velocity really starts at 0, and then as time passes it keeps increasing, but then it stops increasing and it just flattens out. And so that's the difference here. We can see that this is just a straight line. When we don't take air resistance into account, velocity continues to increase indefinitely. But here, when we take air resistance into account, we can see that we reach a maximum velocity, the terminal velocity of the object. And that's it. That's it for these two differential equations.